Okay, so let's talk about radicals. You know, that little checkmark symbol in a math problem that can make your brain just freeze for a second? If you've ever felt that, you are definitely not alone. For so many of us, radicals feel like this weird, complicated thing, but we're about to change that. And I'm not kidding when I say you're not alone. There was actually a study back in 2013 that confirmed what every math teacher already knew. The sight of radicals is often met with, and I quote, groans of disgust. So yeah, that feeling, it's a shared experience. It's a totally common hurdle. But here's a thought. What if that frustration isn't about the math itself, but about how we first learned to look at it? What if there's a core idea so simple it changes everything, turning radicals from a mystery into a tool you can totally master? So let's start right at the beginning. What even is a radical? Let's forget all the complicated rules for just a minute and get right to the one simple idea that unlocks this whole thing. Okay, this right here, this is the key. The term square root is incredibly literal. Imagine you have a square and its area is, say, 25. The root of that square, the length of its side, is 5. So the square root of 25 is 5. That's really it. It's not just some abstract rule. It's a picture. It's about finding the side of a square. And this idea wasn't just invented to make our lives harder in algebra class. Nope. This thing has an amazing history, a story that goes back thousands and thousands of years. The little symbol we use today is actually the result of a really long journey. I mean, just look at this timeline. We're talking about nearly 4,000 years of history here. People in ancient Babylonia and Egypt were messing with square roots way back in 1800 BC. Then the ancient Greeks bumped into them and discovered irrational numbers, which probably blew their minds. And it wasn't until 1525 that a German guy named Christoph Rudolph first printed something that looks like the symbol we use. It's been a long, long road. And this just shows you the symbol itself wasn't just set in stone from day one. It was kind of messy. You can see all these different attempts by mathematicians through the centuries. Some used an R, others used these other weird squiggles. It took a long time to land on the one we all recognize. It just goes to show you math is a language, and it had to evolve. All right, so now that we know the what and the why, let's get into the how. Let's think of the rules of radicals not as a bunch of random commands, but more like a toolkit, a set of tools that helps us work with these sides of squares. So here we go, a classic problem. You look at this and you think, can I just add the 6 and the 54? And the answer is no. It's like trying to add apples and oranges. Right now, the square root of 6 and the square root of 54 are not like terms. So what do? The trick is to simplify first. We have to look inside that 54 and see if there are any perfect squares hiding in there. And yep, there is one, 9. Since 54 is just 9 times 6, we can break it up. And what's the square root of 9? It's 3. So we can pull that 3 out of the radical. It meets up with the 3 that was already there, so we multiply them. 3 times 3 is 9. So now our problem is 2 root 6 plus 9 root 6. Hey, now they're like terms. And our answer is 11 root 6. Okay, on to the next rule that always makes people ask, why do we have to do this? Rationalizing the denominator. Well, there's actually a pretty good reason. Back before everyone had a calculator, trying to divide a number by a crazy long decimal like the square root of 2 was a total nightmare. It's just so much cleaner, so much easier to divide by a nice whole number. Okay, let's try a nice simple example. We've got 3 divided by the square root of 12. Our goal is to get that radical out of the bottom of the fraction. So the move here is to multiply by a clever version of the number 1, the square root of 12 over itself. On the bottom, root 12 times root 12 is just 12. Easy. On the top, we get 3 times the square root of 12. So we have 3 root 12 over 12. But wait, we can simplify that more. The square root of 12 is the same as the square root of 4 times 3, which is 2 root 3. So our numerator is actually 6 root 3 all over 12. And that simplifies down to our final, much cleaner answer, the square root of 3 over 2. But what if the denominator is a bit more complicated? With 2 terms like this one. If we just multiply by root 2, we're still going to have a radical down there. So for this, we need to pull out a special tool from our kit. And that special tool is called the conjugate. It sounds fancy, but the idea is super simple. You just take the expression and flip the sign in the middle. So the conjugate of 5 minus root 2 is 5 plus root 2. And here's where the magic happens. When you multiply something by its conjugate, the middle terms cancel out, and poof, the radical disappears, leaving you with a nice, rational number. So, back to our problem, we multiply the top and the bottom by that conjugate, 5 plus root 2. The bottom becomes 25 minus 2, which is just 23. The top becomes 4 times 5 plus 4 times root 2. And just like that, we're done. The radical is gone from the denominator. Mission accomplished.
So we've been crunching numbers, but let's take a step back and see what these things actually look like. Because radicals don't just sit in equations, they also create their own unique graphs.
So over here on the left, this is your basic square root graph. Starts at 0 and kind of curves up and to the right. Now look at the graph on the right. See what's different? The entire curve just slid over 5 spots to the right. That -5 inside the radical is a signal. It tells the graph to make a move sideways. It's a totally predictable transformation you can see with your own eyes. All right, time for the grand finale. Let's put all of these tools together to actually solve equations. This is where we use everything we've learned to find a mystery number that's trapped inside a radical. And luckily, there's a clear 4-step game plan for this. Step 1, get the radical all by itself on one side of the equation. Step 2, do the opposite of a square root, which is to square both sides. That makes the radical symbol disappear. Step 3, solve the nice simple equation you have left. And step 4, and this one is super important, always check your answer by plugging it back into the original equation, just to make sure it works. Okay, let's do one last challenge. We need to figure out what x is in this equation. The square root of x minus 4 equals 3. All right, let's follow the steps. Is the radical isolated? Yes, it is. So we square both sides. On the left, that gets rid of the radical, leaving us with just x minus 4. On the right, 3 squared is 9. So x minus 4 equals 9. Add 4 to both sides, and our answer is x equals 13. And if we do a quick check, the square root of 13 minus 4 is the square root of 9, which is 3. It works. So, there you have it. We went from a point of frustration to seeing that radicals are way more than just a bunch of rules to memorize. They're a language, one with a 4,000-year-old story that's all about something as simple as the side of a square. Which makes me wonder, what other math concept totally clicked for you once you finally learned where it came from?